Okay, so formal charge is in some ways similar to oxidation states, but in some ways the total opposite of oxidation states. So formal charge is something that we'll use when we're talking about covalent bonding. And the way it's similar to oxidation states is that it's going to be a method that we use to sort of keep track of electrons. It's a quick and easy way to determine how charge is spread out around a particular covalent species, basically molecules or polyatomic ions. So it's sort of a way of within a structure assigning where is the charge concentrated. So is the charge evenly spread out and all of the species have no charge on them? Or within an ion or even a molecule, do some of the atoms actually carry some sort of positive or negative charge based on the number of covalent bonds that they have? So whereas oxidation states was assuming that all things bonded ionically, and tried to assign ownership of electrons 100% to the different atoms within a species. That was useful for trying to figure out which elements had lost and gained electrons so that we could look at redox changes. For formal charge, we're looking not at reactions, but we're looking at the structures of just molecules or polyatomic ions as they are. So we're not concerned about the change in the number of electrons. We're assessing the number of electrons that they currently sort of have ownership over based on the covalent bonding. So in a given Lewis structure, formal charges are always going to be integer numbers. So they'll be whole numbers, negative or positive. This isn't the actual most exact thing that we could do. A lot of times charge is not spread out in sort of integer ways within particles, but that is more complicated than you need to be worried about for the DP chemistry course. So how do you actually calculate a formal charge? It's actually pretty simple. There's an equation you can use. I prefer just to look at the Lewis structures and do it that way. The idea is that each atom owns all of its non-bonding electrons. So if I look at, I have two different structures here for us to walk through the steps for assigning formal charges. So the non-bonding electrons, or the lone pairs, are the ones that we draw as dots. And clearly those only belong in this example to chlorine because they're not being shared with hydrogen. So these 6 electrons here belong to chlorine. We'll start with just the hydrogen chloride example. When atoms are bonding, so they have a bonding pair of electrons, each atom owns one of the pair of electrons. So essentially what we're doing is we're going to ignore electronegativity, and we're just going to assume that the bonds are being shared 100% covalently, so perfectly evenly. So that means that the chlorine sort of owns one of these electrons because it's sharing the pair, so it's as if it owns one of them, and it's as if the hydrogen owns the other. Now what we do to figure out the formal charge is we compare the number of electrons that they own in the structure to the number of valence electrons that they would normally have. So hydrogen normally has 1 valence electron, and I can see that I've given it 1 dot. It basically owns 1 electron in this structure, which means that hydrogen has a formal charge of 0 in this structure. Chlorine is in group 17. It normally has 7 valence electrons. And in this structure, it has ownership of 7 valence electrons. So that matches. And overall, it has a 0 formal charge. And okay, this is good. This is very stable. What we're going to look at is that when you're assigning these formal charges, one of the purposes of them is to sort of assess how stable a given Lewis structure is. Sometimes there's going to be more than one way we could draw a Lewis structure for a molecule or a polyatomic ion, and formal charge is a tool that we can use. It's not perfect, but it's a tool that we can use to try to assess how preferred or how stable a given structure is. So we're always trying to lower charge. Lower charge is going to be more stable. So if both elements can be 0, that's great, and that means it's probably the most stable Lewis structure possible. Also, the sum of the formal charges has to add up to the overall charge on the particle. So since HCl was a molecule with no charge, this works out. 0 plus 0 equals 0. So we've done number 4, and we're all set. If we wanted to do it as an equation, I really think this is more complicated than the other method, but I'll do it an example. Chlorine's number of valence electrons is 7. It had 6 non-bonding electrons, and it was sharing 2 bonding electrons. So half of its bonding electrons belong to it. So minus another 1, and that gives it a formal charge of 0. So if you like an equation, you can use that equation. But essentially, you look for the normal number of bonds for an element. Hydrogen normally makes one bond. Chlorine also normally makes one bond. So when I look at this and they're just making one covalent bond, I immediately know both of them are going to have a formal charge of 0. If you see an element making more than its normal number of bonds, that's going to end up giving it a positive formal charge, essentially for every extra bond that it has. And if something has less than its normal number of bonds, that's going to give it a negative charge for every bond that it's missing. So those are some other sort of quick ways you can try to assess it. Let's do this other example to see an example where there actually is formal charges. So if we look at this one, these two belong only to carbon, and I just kind of split the bonds in half. So these 3 electrons also belong to carbon. That gives this carbon 5 valence electrons. Carbon normally has 4, and if it has an extra valence electron, that means it ends up with a negative charge. So in this molecule, carbon sort of has a little bit of extra electrons, a little bit of extra negative charge surrounding it because of how the bonding is working out. If we go down to the quick ways, normally carbon would make 4 bonds. This is a very weird example for carbon where it's only making 3. And you can see that since it's making 1 less than its normal number of bonds, it ends up with a -1 formal charge. Oxygen, on the other hand, normally makes 2 bonds. In this example, it's making 3. Since it has 1 more than its normal number of bonds, we could predict it's going to have a +1 formal charge. We'll go through just to be sure. It's got these 2 electrons, which it owns, plus it has 1, 2, 3 from the shared ones. That gives it 5. Oxygen has 6 valence electrons normally, and that means it's missing 1. So in this molecule, the carbon ends up with a sort of positive charge associated with its end and a negative charge on the other end. So it gives us some sense of the polarity and how the electrons are spread out. So this is one way to look at polarity. You can see that -1 and +1 obviously cancel and they add up to 0, which is good because this is a neutral molecule. But this is how we would assign formal charges within a molecule. Okay. Just to show you, this also works for polyatomic ions and for expanded octets. Here's an example with a polyatomic ion. So if I go through this, again, depending on the different ways you want to do it, if I look at the hydrogens, each of these hydrogens owns 1 out of the 2 bonding electrons, so they all have formal charges of 0. I could also think of it as hydrogen is making its normal number of bonds. It's making 1 bond, so that means it's going to have a formal charge of 0. Nitrogen normally makes 3 bonds and normally has 5 valence electrons. Right now, the nitrogen is making more bonds than that, which implies it's going to be positively charged for a formal charge. It also only has ownership of 4 electrons instead of its normal 5. So it's missing 1. And so what that means is that the positive charge of this ammonium polyatomic ion seems to be focused around the nitrogen. The nitrogen is carrying the positive charge more than the hydrogens are. So when I have NH4+, if all the hydrogens have a 0 formal charge and the nitrogen has a +1 formal charge, then they add up to the overall charge on the polyatomic ion. In this one, SF4, let's see, we have fluorine on the outside. In expanded octet polyatomic ions or molecules, usually the outer atoms have a normal octet. And have their normal number of bonds. It doesn't have to be that way, but that is the case with this example anyways. Fluorine has 7 valence electrons normally. It's making its normal number of bonds. So all of the fluorines are going to have a 0 formal charge. And if I look at the sulfur in this one, it's got 1, 2, 3, 4, 5, 6. So actually sulfur has its normal number of electrons. So even though it doesn't have its normal number of bonds, so that number of bonds rule is sort of a guideline for standard octet examples. If you count up the electrons that it actually has ownership of, it's also normal. And so that gives this a formal charge of 0. So everything in this structure has a formal charge of 0, which means it's stable and it adds up to the overall charge on SF4. Okay, so what the actual use, as I mentioned before, is that we can use formal charges to assess two different Lewis structures that are both possible for us to draw, and it can help us decide which one is more stable. So the general rule is that the less formal charges we have, the better, because that's more naturally charge is going to spread itself out and try to decrease rather than building up very high charges on different atoms within the molecule. So that's sort of the main guideline of formal charge. Sometimes we actually will end up with more than one structure that has all the same numbers of formal charges in it. And so that's kind of a limitation of formal charge, is that it can't really assess every single example perfectly. And so in those examples, we actually have to go outside of formal charge, and we actually have to consider electronegativity. So formal charge ignores electronegativity, so it's kind of a limitation of it. So rule number 2 is that if you have two structures with the same formal charges, then you want to try to give the more electronegative atoms the negative formal charges, since they are more likely to attract the electrons to them. So just to show you what I mean by this, here's two different ways to draw the polyatomic ion for sulfate. The one on the left follows the octet rule. Everything has a regular octet, whereas the one on the right does the expanded octet rule that only is covered in the HL syllabus. If I go through and assign formal charges, every oxygen has 6 of its own electrons plus 1 that it's sharing. And so in this structure, every single oxygen is carrying a -1 charge. Oxygen's making 1 less than its normal number of bonds, and so that's another way to sort of spot that it has a negative formal charge. The sulfur, on the other hand, has 1, 2, 3, 4 electrons that it has ownership of, as opposed to its normal number of electrons of 6, which means it has a +2 formal charge. So overall, this adds up to 2-, which is the charge, but it looks like there's a lot of formal charge here. Every single atom is carrying a charge. That might not be the best we can do. So if we check this one instead, 1, 2, 3, 4, 5, 6 of these electrons belong to the sulfur. That gives the sulfur a formal charge of 0. These two oxygens, which are double bonded, have formal charges of 0. That's the normal way for oxygen to bond. So both of these oxygens are 0. And then finally, these ones both end up having an extra electron. And so in this structure, these two end up with -1 each. And so that's where the 2- charge comes from. So this structure we would say is preferred because it minimizes the amount of formal charge within the structure. The charge is more spread out this way. So this one is not as good, even though it follows the octet rule. This one seems to be a preferred, more stable Lewis structure. Now in reality, we would recognize that because the pi bonds can actually be in multiple locations, and we could draw resonance structures for sulfate, the pi bonds are actually delocalized across all 4 bonds, and the best picture of this would be to probably give a -1/2 formal charge to all of the oxygen atoms evenly, which would add up to the overall -2 charge. That is not something you're required to do in the DP syllabus, but I just wanted to point it out that although we say this is the best structure, in reality, with the delocalized electrons, it would actually be spread out even more than that, down to like basically half negative charges. So the last thing to point out, obviously, this is one tool that we can use. Their formal charges are not a 100% match of reality, just like oxidation states were sort of a made-up way just to keep track of electrons. There are some positives to it. It can give us a quick sense of how charge is distributed around things that are covalently bonded, and it gives us a tool to assess when we have two different Lewis structures. It gives us a way to decide which one is probably more stable. Downsides, it is a bit inaccurate. It spreads out charge only in integer amounts, which isn't the reality of it. It assumes equal electronegativity. So that's obviously not the case. Atoms have different electronegativities, which affects how charge is spread out. So it's an oversimplification. So we might have inaccuracies about how charge is distributed, and that could lead to misconceptions about things like polarity of molecules as well. Another limitation, which I mentioned before, is that sometimes more than one Lewis structure can end up with the same amount of formal charges, so you can't really decide which is preferred unless you go outside of formal charge and actually consider electronegativity, and then you can figure out which one is more stable. So formal charge, the rules for determining it, and how we can actually use it.